Welcome back to the channel. Have you ever wondered how we measure something as simple as a flat surface? It sounds easy, but in the world of high-precision manufacturing, a flat surface is never truly flat. Today we are diving into the fascinating world of dimensional metrology to understand how we deal with this reality and ensure our parts fit together perfectly. In geometry, a plane is a perfect two-dimensional surface. It's an ideal. But in the real world of manufacturing, nothing is ideal. Parts have microscopic hills, valleys, and curves due to the machining process. We call these imperfections form errors. So how do we measure a wavy surface and call it a single perfect plane? This is where the concepts of a datum and a datum feature come in. The physical imperfect surface is the datum feature, and the perfect theoretical plane we measure from is called the datum. Our job is to create that perfect plane in the virtual world based on the imperfect reality we measure. To measure a part, we need to hold it in a stable, repeatable position in 3D space. Think of it like a tripod. The three legs of the tripod define the stable base. In metrology, we use a datum reference frame, or DRF, to do the same thing. This is a coordinate system of three imaginary perfectly perpendicular planes. We use the most important surface of our part to define the first plane, which we will call the primary datum, or datum A. This is usually the largest, flattest surface. Placing the part on this plane constrains 3 degrees of freedom. It can no longer move up or down, and it cannot pitch or roll. This is the foundation of the famous 3-2-1 principle. The CMM is one of the tools that we use to collect data points. We could measure a plane with just 3 points, but the 3 points can't possibly capture the full picture of our wavy surface. That's why we use scanning. Instead of just touching a few points, the CMM probe drags across the surface, collecting thousands of data points to create a detailed map of the surface's true form. This comprehensive data is what allows our software to create the accurate virtual plane. The standard procedure for a datum plane is to measure it with a multi-line polyline scan. These lines are not random, they are strategically placed near the perimeter of the surface, about 10% away from the edges. Why 4 lines or more? To capture the overall form of the plane and to get a statistical significant data set. And why 10% from the edges? Because the CMMs are subject to a phenomenon called the edge effect. The data collected too close to an edge can be unreliable. By staying away from the boundary, we ensure our data is clean and accurate. Calypso has a crucial rule for when a part is too narrow for a 4-line scan. If a plane is too narrow, you can measure it with 2 lines. Even if it's narrower, you can use a single line. A single line measurement can never be used as primary datum in any way. Even with all the data, how the software constructs the plane matters. There are different mathematical models to choose from, each within a specific purpose. The most common is the least squares plane, or Gaussian plane. This is the statistical best fit plane, minimizing the distance from all the measured points. It is the average plane. Then there's the outer tangential plane. This plane rests on the highest points of the surface, simulating how the part would physically rest on a flat surface. This is crucial for parts that need to be set on a base. Finally, the minimum feature plane touches the lowest points of the surface. This is used when the clearance or minimal material condition is important.